Hello folks, how's it going? Mike coming back at you with yet another video on Foundations of Math 2. In the previous video, we talked about a set of rational numbers and some of the properties and the operations with how those things work. In this video, we're going to talk about irrational numbers, or the non-rational numbers. So at the end of the previous video, we said that we could recognize a natural number if its decimal was either finite or it was infinite but with a repeating pattern. Well, a sense of a definition or something you can look out for to try to determine if a number is irrational is that it's a number that can be represented by a decimal that is neither finite nor has an infinite repeating pattern. Here's some examples of some irrational numbers: the square root of 2, the square root of 3, the cube root of 17, and then that last symbol there may look a little odd. That guy is called pi. If you go on to take higher level math courses, you'll learn what pi is if you have not already yet seen it. We're going to focus on things like the first three above, more specifically the first two, but just in general, square roots or cube roots, things like that. An expression with a radical sign involved is called a radical, just the entire thing overall. The number or numbers or terms underneath the radical sign are called the radicand, just a little term that you want to be sure you keep straight. Radical is everything, the radical sign plus what's underneath it. The radicand is just what's underneath the radical. So we're going to talk about the square root of a number. The square root of a, denoted by this odd-shaped thing here, looks like a V and then a horizontal line after it. And underneath that is a. This is, by definition, the number you have to multiply by itself to get a. Here are some properties of how square roots interact with the various operations that we have. For division and multiplication, we have a couple really handy properties that do get used quite a bit. The product property for square roots, and these properties really hold true to any root whatsoever. It could be cube root or higher level or higher roots, but we're just going to focus on these in the context of the square root for now. But anyway, the product property says that the square root of the product of two numbers is equal to the product of the square roots of those numbers individually. So whenever you're multiplying two things, you can break them up at the multiplication and take the product of their individual square roots. Similarly, the quotient property, if you're going to take the square root of the quotient of two things, that's equal to the quotient of the square roots. And then lastly, adding and or subtracting. You have to be very careful when you are adding or subtracting things that contain square roots. You can only do it as long as the radicands in everything that you're adding or subtracting up is identical. As long as all the radicands are identical, then a times the square root of c plus or minus b times the square root of c is equal to a plus or minus b, then times the square root of c. You're only adding or subtracting the numbers in front of those square roots. You're never actually adding or subtracting the radicals and or the radicands. So we're going to get some practice here, seeing how we use these properties. we're going to use that product property to simplify radicals, specifically these two here, the square root of 50 and the square root of 96. Now, if you're asked to simplify a radical, what you're trying to do is you're trying to find two numbers that multiply to your given radicand such that one of your numbers is a perfect square. And when you take the square root of that perfect square, you just get a natural number. So if I look here at the first sample here, if I look at the square root of 50, I want some number such that if I multiply it by some other number, I get 50, and one of these numbers is a perfect square. Well, I know that 50 is 25 times 2, and I know that 25 is a perfect square, because 5 times 5 gives me 25. So, if I write 50 as the square root of 25 times the square root of 2, and the square root of 25 is 5, then I get 5 times the square root of 2. So this is what we're doing when we're simplifying these guys. We want to rewrite it as a natural number times the square root of some smaller number than what we were given in our radicand. Next one, the square root of 96. This one is a little bit more challenging, but if you think of your squares, 16 is the one we're trying to work with, because 16 times 6 is equal to 96. So I can write the square root of 96 as the square root of 16 times the square root of 6. The square root of 16 is 4, so we have 4 times the square root of 6. So those are just a couple samples using our product property. Let's see some samples where we use our quotient property. Before we do that, let's work in the opposite way. Let's actually find what products of square roots are going to be. So the square root of 7 times the square root of 11. Again, using this guy right here, now we're given this, and we want to turn it into something like this. So all we have to do is we have to take the product of the numbers that are underneath those square roots. So this thing is going to equal the square root of 7 times 11, which is 77. So the square root of 77 is what we can turn that into. Similar kind of thing for this guy here. The square root of 13 times 21, and 13 times 21 is 273. So those are the two different ways we can use our product property. Take a single radical and simplify it, or we can take the product of radicals and turn it into a single radical. Question for you. Is it always true that the square root of the quantity a plus b equals the square root of a plus the square root of b? Is this always true? Well, we may make a conjecture, going all the way back to the first video for the course, that this is. So let's try some test values of a and b, and let's see if this will work. Pick any a value and any b value you want whatsoever. Ideally, pick something nice, just pick natural numbers. So I tried it with a equals 9 and b is equal to 49. So when I do the right-hand side, the square root of a plus the square root of b, square root of 9 plus the square root of 49, That gives me 3 plus 7, which is 10. Now I'm going to do the same thing, but with the left side. I'll plug in 9 and 49 there. So the square root of a plus b then is the square root of 9 plus 49, which is the square root of 58, which if you plug it into your calculator is approximately 7.61577, and there's some more decimal places after that. Clearly, these two numbers are not the same thing. 7.615 blah, 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 and 10 are not the same number. So therefore, we have to say that the square root of a plus b is not equal to the square root of a plus the square root of b. Same kind of thing goes with minus here. If you had a minus sign in there as well, same thing happens. And this is a very, very, very important fact that you want to keep in mind when you're working with square roots. This is a common error that people make. They think, oh, the square root of the sum of two things is equal to the sum of the square roots. Not quite. You can only break it up when you are dividing or when you are multiplying. Now let's see how we can use that quotient property to simplify radicals where we have quotients involved. So we're going to simplify the square root of 56 divided by the square root of 7, as well as the square root of 96 divided by the square root of 4. So first one there, we have the quotient of the square roots. Again, going back to our quotient properties here, if we have the quotient of the square roots, then that's equal to the square root of the quotient of those two things. So I can rewrite that first quantity here as the square root of 56 over 7. Well, if you do 56 divided by 7, you get 8. So you have the square root of 8. And then we can simplify the square root of 8 more. This thing is equal to the square root of 4 times the square root of 2. And the square root of 4 obviously is 2. So that gives us 2 times the square root of 2. Second one here, we're going to do the same kind of thing. The square root of 96 divided by the square root of 4 is equal to the square root of 96 over 4. And 96 over 4 is 24. Now, the square root of 24 is equal to the square root of 4 times the square root of 6. The square root of 4, once again, is 2. So that gives us 2 times the square root of 6. So when we simplify these things, we are fully simplifying them. We are using that product property as well. Just some practice with finding the below difference and or sum. Again, you can only add or subtract radicals when all the radicands are the same. If they are all the same, then you're only adding or subtracting the numbers in front of those radicals, not the radicals and the radicands themselves. So I look at this quantity here. I look at my square roots. The radicands are all the same. They're all just the number 6. So we're good. We can add and or subtract all the terms in here. So I'm just taking the sum or difference of the numbers in front. The 5, the 11, and then we're subtracting the 4 from it. So we have 5 plus 11, which is 16, and 16 minus 4, which is 12. So that is equal to 12 times the square root of 6. Sometimes you see something that looks like this. Sometimes you see a difference or sum where what's inside your radical, aka the radicand, is not all the same as given. And you may think that you can't do anything with it. That's not necessarily the case. If I'm going to ask you to find the difference or sum of things, and the radicands aren't all the same, then it likely means that you can use one of our previous properties to change these terms so that all their radicands are the same. I have a 28, I have a 7, and I have a 175 here. Typically, what you're going to do is you are going to deal with the larger of the radicands and leave the smallest radicand all by itself. And you're going to try to take these things here and change how they look so that the number that's inside of our radical is going to be this 7 here. So I know that 28 is 4 times 7. So the square root of 28 is going to be the square root of 4 times the square root of 7. Then we're going to have that minus 3 times the square root of 7. Minus, and 175. 175 is equal to 7 times 25. So this is going to be equal to the square root of 25 times the square root of 7. And now these things here, the square root of 4 and the square root of 25, those are nice natural numbers. So we can make that substitution, or that we can do that calculation, and we see that in the end, the square root of 28 is equal to 2 times the square root of 7, and the square root of 175 is equal to 5 times the square root of 7. So now we've changed it so that each one of our terms has the same radicand, and thus the same radical, and then we can just take the difference of all these numbers in front. 2 minus 3 is -1, minus 5 more is -6. So this quantity is equal to -6 times the square root of 7. So that one is certainly a little bit more challenging, a little bit more work that you have to do, but still overall pretty reasonable. If you're asked to find the difference or sum, and the radicands are not all the same, then it's because you can use our product and our quotient properties to change it so that all your radicals are identical. Last big thing I want to talk about in this PowerPoint. Sometimes we have a radical in the denominator of our fraction. And this is ugly, it's bad, it's just not something we really want to see. So how do we deal with that? How do we get that radical out of the bottom of our fraction? We do something called rationalizing the denominator. And when we rationalize a denominator, we're going to multiply on the top and bottom of the fraction by the denominator of the given quantity, that is to say, the radical, and then we're going to simplify it. So simply multiply on the top and bottom of your fraction by the bottom of your fraction. That's all you have to do. Really straightforward. So we're going to rationalize these two quantities here. 13 divided by the square root of 8, and negative 6 divided by the square root of 26. So working with this first guy here, we see that we have square root of 8 on the bottom. I'm just going to multiply on the top and on the bottom by the square root of 8. And all I'm doing is I'm just multiplying this fraction by a 1. So I'm not changing the quantity that I have, I'm just changing how it looks. And we mentioned in a previous video that it's okay to change how it looks as long as you're not changing the quantity that you have. So here, that's exactly what I did. Square root of 8 divided by the square root of 8. We now have two fractions here. We're multiplying fractions, multiply the tops, and multiply the bottoms. So that gives me 13 times the square root of 8 all over 8. If you could simplify further at this point, then you would do so, but in this particular instance, we cannot. Next one, negative 6 divided by the square root of 26. We're going to do the exact same thing, but now we're multiplying on the top and bottom by the square root of 26. But first, the square root of 8 here is equal to 2 times the square root of 2. And we actually can simplify that out further. That is my apology, my bad. So we actually can simplify that further to 13 times the square root of 2 all over 4. Now we're going to go on to our next one. Now we're going to do negative 6 divided by the square root of 26. And we're going to do same thing, multiply on top and bottom by that radical there. So that gives us negative 6 times the square root of 26 divided by 26. Now the square root of 26, we can't pull any nice square out of that. So we're just going to leave that radical as is. But between 6 and 26, we have a common factor of 2, which we can pull out. So that gives me negative 3 times the square root of 26 divided by 13. So this is how we rationalize the denominator when we have square roots popping up in there. This concludes our video on irrational numbers. In the next video, we are going to take a look at a larger set, the set of all real numbers. Guys, if you have any questions or comments, please be sure to reach out to me. Emails, texts, SOSs, signals of any shape or form or kind, whatever you have to do. Otherwise, until the next video, take it easy, guys.